Hello everyone, my name is Fernando. I'm responsible for the electronics instrumentation group at Brazilian Singleton Light Source. And in this talk, I will give an overview of electronics development for the Sirius bin lines. So I will give you a quick overview about the group, uh, the importance of electronics development for the bin lines. I will show two examples of demands in electronics, discussing the development and some important results. In the end, I will add some reflections and future plans for this field. From 2013 to 2020, the GAE group took care of the maintenance of the UVX bin lines. I mean the bin lines from our old machine. And in that time also we started the design of the common systems for the series bin lines, such as the automation system like EPS, Equipment Protection System, the PPS, Personal Protection System, also the electrical system, and the control infrastructure. So since last February, we splitted the group, creating the GIE group, the Electronics Instrumentation Group, that is a young team with a focus on the electronics development to solve the most challenges of data acquisition coming from the experiments using synchrotron radiation. So electronics is an essential part of the bin line. It's pretty much necessary to measure all the physical variables like pressure, intensities, current, voltage, temperature, making controls and feedbacks. In the last 18 months, we have developed more than 15 devices or electronic systems to integrate commercial hardware to our control system, or circuits to solve problems that commercial products can't. Since the new group was formed, a new responsibility is to provide support in electronics for the development of X-ray area detectors, working together with the detector groups. So in this presentation, I would like to talk about 5 instruments that is part of a family of low current measurement equipments. At the bin line, one of the most common signal generated by interaction of photon beam uh, and some materials are the low intensity electrical currents coming from devices such as photodiodes, ionization chambers, electron collectors, and even beam position monitors. The signal is pretty small, ranging from few picoamps to few milliamps. At the UVX, we had 18 bin lines and 30 channels of current for all the bin lines. Uh, at Sirius, we are planning to have 14 bin lines in the first 1A and 1B phase, and we will have at least 200 channels, which makes this type of measurement very important in terms of cost. Uh, we have a lot of commercial instruments, each one with your own characteristics, some of them with USB, serial, or Ethernet connection, or just an analog output that we prefer, because a few years ago we have decided to use a universal data acquisition hardware that allow us to have all the signals in one controller and make any type of digital signal processing and synchronization. For this reason, we have used many current amplifiers in UVX, taking into account this large number of devices that we needed in the bin lines, in the new bin lines. Uh, So, and also considering that we need to integrate all the signals in the same controller, we decided to develop a general purpose, simplified version of current to voltage converter with relatively low cost and with a reasonable performance, always covering the minimum needs of the bin lines. And okay, we believe that this is very important for us to understand all the details about this kind of measurement, because in the future we also know that the scientists will ask for a better resolution, lower currents, or fast equipments. Let's talk about the one-channel current amplifier solution. At UVX, we had a lot of current amplifiers from American vendor, and we use this as our benchmark instrument. We wrote the detailed specification, taking into account the binline needs and the most common feature in the commercial options. Uh, Basically, the amplifier must measure bipolar currents from few picoamps to few milliamps with a good resolution, reaching bandwidth as up to 1 kilohertz, and good accuracy in terms of accuracy and a very low temperature drift. There are a few well-known methods to measure small currents, each one with positive points and drawbacks. But we did the classical topology of a transimpedance amplifier. That's a circuit used also in the commercial instruments like the famous Kitley ammeters. Uh, Even though it's a classic method, this type of circuit is very sensitive and susceptible to many sources of errors, like surface leakage, triboelectric and electrostatic coupling, electromagnetic interference, and even sensitive to cosmic X-ray at very low current levels, and let's say in very is the smallest range of let's say below the femtoamp scale. Uh, in this circuit, the noise is dominated. The resolution is dominated by the thermal noise in the feedback resistor. In the end, this is the physical limit of these circuits. Okay, here is the one channel amplifier in the final enclosure. Look that we got success to have a pretty small device that we can put very close to the binline component, which is an advantage to avoid long cables, and also because we have a very good temperature control inside our hutches, which also helps to get a very stable measurement in terms of drift. I mean, the circuit is very immune to temperature variations. To use the amplifier, we need to supply the circuits with a ultra-low noise power supply that we also developed here. And to choose the range, one of the 5 ranges that you want, we have also developed Ethernet range selector that send digital signals to the amplifier to proper select the proper resistor in the feedback network in the transimpedance circuit here. And also as an option to the standard commercial controller, there are a few places in the bin line that it's impractical to have a standard data acquisition hardware. And then we did the prototype of Ethernet ADC converter with an integrated range selector that could be used as an option if you don't have the commercial hardware available in this in that region in the bin line. So here is a picture of the assembled board. Note that we took care with surface leakage, putting some openings in the PCB, mainly in the input current path, and also a presence of additional internal shielding, because this circuit is very sensitive respect to the mains frequency. In Brazil, we have a 60 hertz. The cost to manufacture in Brazil, it's about $400, including the partial cost of the low noise power supply that can fit 4 amplifiers like that, and the cost of the range selector. Due to the time of this presentation, I'd like to show a simple comparison noise data between the developed amplifier and the commercial hard that we used as our benchmark. This plot is a noise spectral density that is helped us to compare noise of different systems. In left, we have our RMS current noise per square root of the bandwidth, and in the horizontal scale, we have frequency. The origin signal is the noise from the commercial products, the commercial amplifier, and the blue line is the current amplifier developed by the electronic instrumentation group. We can see that we got success to stay more immune to the mains frequency. You can see these peaks of 60 hertz in their harmonics. You can see also that the noise in this region from very low frequency to 100 hertz is a bit lower than the commercial product. In the 5 picoamp range, we have basically few femtoamps resolution. That it's a very good resolution, taking into account the simplicity of the circuit. Just for curiosity, I put here also the data from the most expensive equipment that I showed in that list on the beginning of this presentation. That it's a electrometer from GIE, and you see that there is no secret. You pay the price to get resolutions below this level. I mean below the femtoamp range. You enter in a region that we can start to talk about counting electrons. You know, we can talk in thousands of electrons per second. Okay, that's the price we need to pay to get the resolutions better than we got. Okay, the status, we have 20 installed units, 50 is under production. During the pandemic, we had a lot of problems with component supplies, and there are few components missing in the market, so we needed to redesign this board. And what is missing, I guess, after we receive the last 50 units, we need to make a final integration with Apex. I mean, uh, to have a very good user interface that you can control all the offsets, correct gain, and all the all the parameters you want to adjust to have a very good acquisition, signal acquisition at the bin line. So, as I said before, we we have an estimative of 200 channels of current in the bin lines, and 120 will come from the one channel amplifier. But 80 channels we must to group in electronics with more channels available, because usually we have for example slits that has four measurements, and then would be great to have an instrument with at least four channels. That this idea I would like to show right now. For the four channels options, we also have a benchmarks instrument that we use it to understand what we need for an instrument like that. We also wrote a very detailed specification, talking with the people from the bin lines. The commercial product costs us around $7,000. Here you can see what is the idea of this instrument. We use the same circuit from the one channel amplifier. I mean, the front end, the analog part is the same, so this is an advantage. But here we put also 24 bits bipolar sigma delta ADC, analog to digital converter, and a microcontroller to integrate the solution with Ethernet connections. So we have the same scales we have in the one channel option, but also we have an interesting feature that we allow us to have a pretty good isolation from the ground, that makes then we have the possibility to apply high voltage signals to bias the sample or the device under test. So you can see the picture of the assembled board. We can produce this electronics in Brazil in a cost of about $1,500. Again, counting into account the low noise power supply. You can see the four channels, the shielding of the individual channels, and then input-output connectors. In a very preliminary result, I would like to show the same graph. I mean, it's a noise spectral density, but not in the small scale, in the biggest scale. As you can see, we also get success to have a more immune circuit. But if you look, the blue line just stop it in 500 hertz, because we have a very preliminary version of the firmware that cannot sample the signals above the sampling frequency of 1 kilohertz. That's a picture that show that we not only show beautiful pictures, but we are fighting to have a very good results in all the scales. with a final version of the very functional firmware. So the status, we have just one prototype assembled. Again, this electronics is under redesign due to the lack of components in the market. So we are trying to find a better solution to redesign using components that we can find easily. We need to finish and overcome this problem in the sampling frequency, the maximum sampling frequency, and then we need to enter in an extensive test phase, and then start to plan the production and do the final integration with our control system. So here is the cost comparison. It's not the purpose of this presentation, but it's just to show that we got a reduction of more than $400,000 producing this electronics in Brazil, and not only using commercial products. That's we think it's a very good result. This is the last slide of my presentation. I guess we can reflect from some points in making the reflection of this young group. We need to finish the developments to fully attend the needs of these new 14 beam lines. This family of low current products solves 95% of the beamline needs and consolidate the knowledge for comprehension and customization of more challenge needs in the near future. With instrumentation challenges will increase as the experiments evolves naturally. We need to continue the commission of the diagnostics and the devices in beamline, in the operating beamlines. We increase the interaction with other groups that works with electronics, like the diagnostics group, and prepare the team with the lack expertise like FPGA and complex digital signal processing. Due to the complexity of the area detectors, the group must also increase the workforce in the detectors development to attend the demands for the actual and future detectors. In this presentation, I didn't mention any detail about detectors because I guess people from detector group will show in more details.